is Chintan Patel and welcome back to the video lecture series of the fundamentals of machine design. In this lecture, we are going to see further moment of inertia derivations and a list of formula. These are the derivations which you need to remember in order to calculate the example easily. So, at the end of the derivations, we will see a table of the formula which you need to remember in order to calculate the examples flawlessly. Okay, so pay attention a little bit more because this will help you to understand the moment of inertia very deeply. Okay, so let's get started with the first derivation, and that is the derivation of the moment of inertia of a circle. So we will see this circle as a basic component, and as you can see, the diagram indicates that the circle is having the diameter d. The centroid or the center of gravity of the circle is at the center point, and the axis x-axis and y-y are the centroidal axis of the circle. So our first step is to find out the area of that circle. So we have taken an elemental strip. As you can see in this diagram, the elemental strip is having the thickness, that is the dx, and it is having the radius of the x from the center of the circle. So if you are your intention is to find out the area of that elemental ring, that area is nothing but the 2 pi x into dx. How we have calculated this area? That is nothing but the perimeter. This is the perimeter into the thickness. That is the basic formula of the calculating the area of the ring. Okay, so or the plane ring. So we have calculated the area of that elemental ring. Now our moment of inertia of the whole section about the axis passing through the O and perpendicular to the paper, that is nothing but the z axis, which cannot be shown in your diagram. But if you want to see that axis, that can be seen like this, okay, which is perpendicular to your screen. Okay, now if you want to find out the moment of inertia about the z axis, then you need to calculate the using the basic formula of the moment of inertia, and that is nothing but the 2 pi x into dx, that is the area into distance from that z axis. Why we have taken the distance from the z axis? Because this distance must be the perpendicular distance from the axis. As you can see, if you consider this x distance, that is not perpendicular to the x or any y distance. Okay, so in order to calculate the perpendicular distance, there is the only one choice, that is not nothing but the z axis. So this distance is perpendicular to the z axis, and that's why this gives the answer of the moment of inertia about the z axis. So if you calculate the integration, you will need to apply the limits for that integration. As you can see, the z passes from this center, and that's why the z is the reference, and all the distance on the z will be 0. So the maximum distance of the elemental ring or the circle is d by 2, because it will be equal to the radius of the circle. Okay, so the limits will be 0 to d by 2, minimum distance to maximum distance. Okay, so these are the limits for our integration. Now identify the variable and the constant so that you can carry out the integration easily. As we can see dx over here, so our variable is x and 2 pi will be our constants. If you keep these constants out of the integration, you will have to integrate the x cube, and the integration of x cube is nothing but the x raised to 4 by 4. So if you apply the limits in that particular integration, you will have to simplify this equation. After the simplification, you will get the answer of the izz as a pi by 32 d raised to 4, and that is nothing but the polar moment of inertia, and pi by 32 d raised to 4. So this was our basic formula of the polar moment of inertia. Now what we are going to do next, as the circular section is symmetrical with respect to all the axes, whether it is a x-axis or a y-axis or a z-axis, Ixx and Iyy will be equal. because both the distance about the x and the y axis are equal, because the figure is symmetrical, and that's why the value of the moment of inertia about the x axis and the y axis are the same. Okay, so whenever you identify the symmetricity about any axis, your example is going to be shortened, or the length of the example will be reduced if you identify the symmetricity of any figure. So this will help you if you practice this kind of if you practice to identify the symmetricity of your figure, it will help you to reduce the length of the example and save some time in your examination. Okay, using the theorem of perpendicular axis theorem, we have learned the theorem of the perpendicular axis theorem in the previous lectures. So you should remember that theorem, that is nothing but the Izz equals to Ixx plus Iyy. As we have already seen that Ixx and Iyy are equal, so Ixx is equals to Iyy. We know this both values are equal, and that's why we can write it as a 2 times Ixx or 2 times Iyy, both are the same. Now we know the value of the Izz. Now what is the value of Izz? It is nothing but the pi by 32 d raised to 4, which is already derived over here. Now if you want to find out the Ixx and Iyy, then make them as a subject, and 1 by 2 into Izz will give you the answer. So simplify that equation, and that will give you the answer as a pi by 64, that d raised to 4. And this is the formula whenever your circle is going to be in the center of the picture, then you will have to utilize the Ixx and Iyy as a pi by 64 d raised to 4 or a pi by 4 r raised to 4 as your formula. If you remember this formula, it will be easier for you to calculate the moment of inertia of the circle about x and the y axis passing through the center. So this was the basic derivation of a circle. Now we will see another derivation, and which is the moment of inertia of a semicircle. So a semicircle is the half part of the circle. So there might be the question in any student's mind that if we know the moment of inertia of the circle and the semicircle is exactly the half of the circle, then why don't we just divide the whole moment of inertia into the half? The formula of the moment of inertia can be easily calculated by dividing it by 2. But in case of the centroidal axis, it might be different. When you see this diagram, then you will understand it. So first you need to pay attention on the diagram, that we know that the axis moment of inertia is dependent on the axis only, and if your axis is getting changed, your distance from the reference axis will be different, and that's why your moment of inertia will be changed. So first of all, we will see the moment of inertia about the diametric base of the semicircle. So what is the diametric base of the semicircle? The diameter itself, and the diameter itself is represented by the AB. So we are considering the upper portion of the semicircle. Okay, this bottom part is nothing but the left cutout portion of the circle. Okay, now here it is nothing but we have taken it as a reference of the circle. Okay, so what will be the centroid of a semicircle from the base? So the centroid will be at this particular point, and this particular point is having the distance from the base as a 4r upon 3 pi. This was the basic formula of the center of gravity or a centroid, and now we will utilize this formula in order to calculate the moment of inertia about the base axis. Okay, so base axis, as you can see, this is the base axis or the AB axis. This was the centroidal axis for the whole circle, but our intention is to find out the moment of inertia of a semicircle. We are not considering the whole circle. Okay, first this was the centroidal axis for a circle, not for the semicircle. For the semicircle, this is a diametral base axis. This is not a centroidal axis for the semicircle. So first what we are going to do, the axis is the same. whether it is for the circle or the semicircle. The axis is not changed, and that's why distance for this particular axis will be the same as in the previous slide, and that's why the distance are unaltered or unchanged, and that's why the moment of the area is only cut out as a half. Our area is reduced to the half, and that's why our moment of inertia will be directly divided by 2, and we will get the answer of the moment of inertia of a semicircle. As you can see, the procedure itself indicates that the moment of inertia about the AB axis of a semicircle is nothing but the 1 by 2 of the moment of inertia of the circle, because the area is reduced by the half portion, by reduced to the half part. Okay, we have considered only the half part of the area of the circle, and that's why the moment of inertia of that circle will be half of the moment of inertia of that circle. Okay, so semicircle will be half of the moment of inertia of that circle, and if you simplify this equation, you will get the answer as a pi by 128 d raised to 4. That is the final answer of the moment of inertia of the semicircle about the base. Okay, now our intention is to find out moment of inertia of the section through its center of gravity. Now, if you know the center of gravity, where the center of gravity lies, the center of gravity lies at the distance 4r upon 3 pi from the base. Okay, here our center of gravity lies. So our intention is to find out the moment of inertia about an axis which passes from the center of gravity. So what we are going to do, we are going to utilize the parallel axis theorem. So what is the parallel axis theorem? Parallel axis theorem is nothing but IAB equals to IXX plus AH square. We know the value of IAB, we know the value of A and H. Then the only unknown which is remained in this equation, that is IXX. So this was the very basic term which we are going to utilize for the IXX and IAB. If you put the value of IAB as a pi by 8 into r raised to 4, keeping IXX as a constant, then area of the semicircle is 1 by 2 pi r square, and distance that is 4r upon 3 pi. Distance square is needed to be applied in your put in your equation. Now if you make IXX as a subject and take the remaining terms into the another side, then your equation would look like this. Now if you simplify that equation, the answer will be 0.10 r raised to 4. And that will be somewhat similar like 0.11 r raised to 4. So this is nothing but the formula of the moment of inertia about the axis passing through the centroid IXX. Okay, so IXX is nothing but the 0.11 r raised to 4 for a semicircle of a radius r. Okay, so this was the basic formula. The moment of inertia about the symmetrical axis YY is pi by 8 r raised to 4. Similarly, we have done this kind of a derivation, and about the XX axis, that is 0.11 r raised to 4. So if you remember those formula, this is a very basic shape, that is semicircle. You will require these formulas for your examples. Okay, so learn this formula by heart. We will see this derivation in your examples. So now we will see one of the basic definition of this chapter, which is nothing but the section modulus. Now what is section modulus? Section modulus is the ratio of moment of inertia of any section about its neutral axis to the distance of extreme fiber from the neutral axis. It is denoted by Z, and this is nothing but the ratio, and its SI unit of the section modulus is mm cube or centimeter cube. As you can see, the Z can be represented by I by Y. It is the ratio of moment of inertia upon extreme distance. We know that a moment of inertia can be written in terms of mm raised to 4, and distance can be written in terms of mm. So the final unit for the Z would comes out to be mm raised to 3. So this is our basic formula or basic unit of the section modulus. Okay, so now what we are going to do, we will see the section modulus. We have seen this section modulus definition. Now we will see the list of formula. So what are the list of formulas? These are the table in which we have written the formulas for the centroidal axis like IXX, IYY for the different shapes like a rectangular shape, triangular shape, circle, semicircle, like that. So you need to remember those formulas for IXX and IYY because whenever in your examples it is required to apply the parallel axis theorem, that IXX and IYY will not be given in your given data. You need to remember that particular IXX and IYY, and if you remember those formula, then and then you will be able to apply the parallel axis theorem. So for the parallel axis theorem, you need to remember those formula. Now how these formula have come or how these formula are derived, we have seen all those derivations in the previous slides, okay, and in the previous lectures. If you need a reference, then you can get those reference from the previous slide and the lectures. But now the derivations are only important for the theoretical part. Now we are going to prepare for the example point of view. Now for the example, you need to remember those equations. The derivation of the equation is already been discussed. Now we will discuss about the equation and how we are going to solve the examples. Okay, so first of all, the first shape is nothing but the rectangular shape. As you can see, the x-axis axis is passing from the center of this rectangle, and y-axis is also passing from the center of the rectangle, and that's why we will see the moment of inertia about both the centroidal axis. So if you want to find out the moment of inertia IXX about IXX about the x-axis, we have seen the formula, that is BD cubed by 12. Similarly, if you want to find out the moment of inertia about the y-axis, then our formula would be dB cubed by 12. So these formulas have already been discussed in the previous derivations. I am providing you this table just to summarize the list of formulas so that you can remember that list of formula. Okay, now we will see the semicircle. In the previous slide, just we have derived a formula for the semicircle, and for the semicircle IXX is given as a 0.11 r raised to 4 and IYY is pi by 8 d r raised to 4. So for the quarter circle, the same method can be applied, and the formula for x and y is given by this. Similarly, if you apply the same method for the circle, we have seen the first slide for the circle, and we know the formula for the IXX and IYY both are the same, and that is nothing but the pi by 64 d raised to 4 for both of the axes. Okay, so this was the basic shapes. Now we will see the formulas for triangular shape and square shape. Okay, so what are the formulas for the triangular square shape first? For the square, both the sides of the rectangle, if the sides of the rectangle are same, we can say it as a square. Okay, so B and D, there is no B and D, only one side length is given, that is A. So if you replace the B and D, you will get the answer as A raised to 4. A raised to 4, and as the square is also symmetrical about the x and the y axis, you will get the answer of the IXX and IYY as the same, that is A raised to 4 by 12. Now if you consider a triangle, isosceles triangle, now this is one of the type which can be asked in your example. So you need to identify whether your triangle is an isosceles or a right angle triangle. First you have identified if your triangle is isosceles, your basic formula for the IXX will be BH cubed by 36, and if you are asked to find out the moment of inertia about the AB axis, that is BH cubed by 12. Now if our intention is to find out the moment of inertia about the YY axis, then HB cubed by 48 will be our formula. Now if you consider the right angle triangle, for the right angle triangle, the IXX formula is a BH cubed by 36, and Iyy formula will be hp cube by 36. All the formulas have been already discussed in your previous derivations, and this is the list of formulas so that you can learn these formulas for the example, for the preparation of the example. So before starting the example, you must learn those concepts of the moment of inertia from the previous lectures, and we will see the method of examples in the upcoming lecture so that you can identify the basic terms, formulas and theorems, and adapt that method to calculate the examples. So we conclude our lecture over here. Till then, thank you.